This question is called correlation of max and min. It says let x1 and x2 be independent and identically distributed random variables with uniform distribution between 0 and 1. Y is the minimum of x1 and x2, and z is the maximum of x1 and x2. What is the probability of y being at least some number y, given that z is at most some number z, for any y and z, the numbers being between 0 and 1? What is the correlation of y and z? So the first part asks us probability of y, which is the minimum, the smaller number being more than y, given that the larger number is at most z, some number z. So if the smaller number is more than y, given the larger number is at most z, then x1 and x2 are both falling in between y and z. X1 and x2 will be at least y and at most z. Because if we're saying given the larger number is at most z, then we're saying that the larger number cannot be more than z. And we already know here the small number has to be at least y. So we're saying the probability of this occurring, of x1 and x2 being at least y and at most z. Because if the smaller number is at least y, then the larger number has to be more than y, right? At least y as well. So, and also given that the bigger number is at most z, the smaller number must also be at most z. So we have to find this, but it says given that the larger number is at most z. So so the conditional probability goes like this. Probability of A given B is the probability of A and B over the probability of B. The probability of A and B is right here, that they're both between y and z. And the probability of B is going to be the chance that the probability that z is at most z. Okay, so on a number line from 0 to 1, because that's what our distribution is like the support is 0 to 1. We're saying, okay, we have some y here and some z here. We need both of these random variables, like x1 and x2, to be between y and z. So the probability that x1, let's say, is between y and z is going to be the size of this length, right? The gap between y and z is going to be also the probability that x1 is in between y and z. Why? Because if we're from 0 to 1, then this portion, aka z minus y, represents the portion of 1 that we're allowed to be in. And if it's the portion of 1 that we're allowed to be in, then, and if there's equal chance of landing anywhere in this range or in this like span, then the chance of landing in this range will be the length of this range or this span. So the chance that x1 is between y and z will be the length itself, so z minus y. The probability that, and then x2 will be the same thing, right? Because they're independent, and they have the same distribution, that's identical distribution. And so will this, right? And so the chance that they both are in between y and z will just be multiplying these probabilities together. So, and that will be z minus y squared. Now, the other portion says the probability that the maximum, the bigger number, is at most z. So let's draw another number line here. For the bigger number to be at most z, that means both of the numbers cannot exceed z. And so the chance that one of the numbers is at most z will be the length of the portion, as we already discussed y. The length of the portion here is just z. And for x2, same thing, z. Y is, we have to care about both. We have to say if the maximum is at most z, then the other number, the min, right, the smaller number, has to be also at most z. So we have to say that both must meet that criteria. And so in this case, the answer is z squared. So the overall probability is z minus y squared over z squared. And that's the probability of y being at least y, given that z is at most z. Okay. Now for the second part, it asks for the correlation. I'm going to copy this and bring it down. So correlation will be, this is the correlation coefficient, or I think it's coefficient. It will be the covariance of y and z over the square root of the variance of y times the variance of z. Okay. So covariance of yz is the expected value of yz minus the expected value of y times the expected value of z. So here's where it gets interesting. Yz is going to be the min and the max. So we're saying yz is the same as zy. So it doesn't matter which one's which, right? And in the case where we only have two random variables, x1 and x2, one will be the max and one will be the min. We don't care about which one's which because it's, I don't know what that property is, but like, it doesn't matter the order, commutative, something like that. So basically I'm saying that this is the equivalent of saying x1, x2, or x2, x1, which is just saying that we can replace yz in this case with the random variables themselves, x1, x2, and this is easier for us because we know the expectation of x1, x2 more easy than we know the expectation of y and z, because x1 and x2 follow a basic uniform distribution between 0 and 1. Meanwhile, y and z follow some extra traits like min and max. So we can like convert this to x1 and x2, and that is just the same thing. Since they're independent, we can just say it's equal to expectation of x1 times expectation of x2. Cool. Expectation of x1 is 1/2 because you're gonna fall between, like, you're gonna fall if you're between 0 and 1. The expected value you're gonna fall on is gonna be the halfway mark. It's like 1 minus b over a or something, or what was it? It was like, I forgot the PMF or the PDF of that, but yeah. So that's the first part. Expected value of y is where it gets a little more tricky. So first we have to find the probability density function of this and integrate over the support. So what is the probability density function of y? Well, you have to take the cumulative distribution function, which tells you the mass, take the derivative of that, and that gets you the probability density, because density is the derivative of mass, and cumulative distribution is used for this case. So f of y of y prime is equal to the PMF of PDF of y. So what is the cumulative distribution function of this? Well, if you have the number line and we have some y was the minimum of the two random variables. We have the problem right here. And so the probability So first of all, what is the cumulative distribution function? If you plug in some value, right, for n, it means that the probability that y is at most n. And that's a little tricky for minimums because it's hard to conceptualize. We're saying that at least one of the numbers has to be at least n, which is a little hard to think about. So instead we can like flip the question and say, okay, what's the complement of this? So the complement of y being at most n is the probability that y is at least n, and do 1 minus that to get the complement of the complement. 1 minus this. And this is easier because in the case of minimums, you're more easily able to find the probability of y being greater than n, which in this case n will be the minimum. So if n is the minimum, the probability that we are more than it, right here, that we're more than this value of n, well, if this part is n, we can land anywhere from n to 1. And we already mentioned that the length will be the probability. And so this length right here is 1 minus n. Cool. So we're saying that and that's for one of the variables. That's for x1, let's say. That has to happen both times, right? Probability of y being more than n is the same thing as saying x1 and x2 being more than n. And in this case, we just take what we just got, 1 minus n, and we multiply it by itself because they're independent and they have the same distribution, so we can just multiply the probabilities together for them both occurring. So we get 1 minus n whole thing squared. For take the derivative of this, we get 2 1 minus n. That's the PDF of this. And now for x, same thing. I'm gonna go take this a little faster. We're saying we want the CDF of x first, and that's just saying the probability that x is at least n, and the probability that, and that means that, x is at most n, and since this is the maximum, we're gonna find that more easily because, hey, same thing, right? We're trying to find the maximum, and this kind of has like the same probability appearance, right? To find the maximum, that means that every number has to have, was it z? Sorry, it's not x, z. Both x1 and x2 have to be at most n, and so that we are trying to find the probability that x1 and x2 both fall into this length of n. And so we have 2 of these, so we have n squared. The derivative of that will be 2n. The expectation of this will be the integral across the support from 0 to 1 of the value at the support we're currently at. So n times, this is for us to do the y case first, times the PDF at that point, which will be 2 times 1 minus n dn. And take out the 2 and the integral from 0 to 1 of n minus n squared dn. 2 out here. Get 1/2 n squared minus 1/3 n cubed from 0 to 1 times 2. So you get 2 times 1/6, which is 1/3. And for the case of z, integral from 0 to 1 of n times 2n dn, take out the 2, you get 1/3 n cubed from 0 to 1, and so you get 2/3. Expectation of z, expectation of y. And so here you get, like, this is the equation we had previously, right? So we had 1/4 previously minus, now expectation of y is 1/3. Expectation of z is 2/3. So you have 1/4 minus 2/9, right? Okay. Times 9 is 9/36 minus 8/36. So 1/36. Cool. And now we're going to find the variance of y and z. That's the numerator we have right here. Now for the denominator, the variance of y is the expectation of y squared minus the expectation of y. So the whole thing squared? I'm not sure. I'll check after. Okay. Expectation of y squared is going to be the integral we did earlier, but instead of plugging n here, you plug in n squared. So you go 0 to 1 of n squared. Probably gotta take out the 2 already from before, like we did before. And it's 2 times 1, 1 minus n, the n. We do n squared here because the expectation of a function of n is going to be that function times the value at that support. Okay. Now we go cubed, so it's 1/3 n cubed minus 1/4 n for the power of 4. And that's 1/12. 2 times that is 1/6. And then expectation of y we said was 1/3. Is that legit? 1/6 minus. Okay, expectation of whole thing squared. Yeah. Okay. So it's going to be 1/6 minus 1/9, 3/18 minus 2/18. Going to be 1/18. And then for the variance of x, or z, expectation of z squared minus expectation of z whole thing squared. Integral from 0 to 1 of n squared. And was it n squared again? Or 2n here. dn 2 1/3 n, or 1/4. Wait, no, 1/3. Together 2, it's n cubed. 1/4 n to the power of 4 from 0 to 1. So here's 1/2. And then expectation of z we said was 2/3. So 1/2 minus 4/9 and 9/18 minus 8/18 is 1/18. And so the numerator we said was 1/36. This is for the correlation function, right? Look at it right here. We just found the variance of y and the variance of z. And we can plug that in here. Numerator was 1/36. Denominator is the square root of 1/18 times 1/18. And so it's 1/36 over 1/18, which equals 1/2. And that's the answer for the correlation. This is the answer for the probability. Bit of a longer one, but yeah, that's the final answer. Or final answers.